I'm happy to announce our next speaker. Gabriele Rembado from the Hausdorff Institute in Bonn will tell us about the geometry and quantization of modular spaces of connections on Riemann surfaces.
Thank you very much. To the organizer for making this possible, despite all the regulation and so on, and also for accepting this short contributed talk. So I am going to share, as you see, my iPad, and basically have a few notes prepared. I'm going to talk about geometry and quantizations of certain modular spaces of connections on Riemann surfaces. And as explained in the abstract, I would like to start from non-singular one, so smooth or holomorphic connections. But what I actually would like to talk about are connections having singularities. So we will have a first part where I introduce such modular spaces of singular connections in the classical world. So essentially introducing modular spaces of such. And then the quantum theory. So where somehow I will explain how to quantize them. So before doing this, let's start from the non-singular world very briefly. So part 0 is going to be this brief recall about geometry quantization of modular spaces of smooth connections. Okay, so many people have studied those. So many people have looked at principal bundles having flat connections on them, smooth, let's say, right now. And by taking the monodromy data, this is equivalent to considering representations of the fundamental group of the base. Here it's going to be a surface. Okay, so many people have studied spaces of representations of fundamental groups of surfaces. Let me phrase this more precisely. So please consider sigma, which is a closed orientable smooth surface, and kappa, which is going to be a compactly group, say connected and simply connected. And of course, we should think of SUM and SLMC as the more natural pair. And then we have seen such diagrams, such arrows and identifications in different places. So we have some modular space MFL, like flat. This is the modular space of flat connections on the trivial principle K bundle over sigma. So you have this for the compact group. So I consider isomorphism classes, or if you prefer, gauge classes. And as I said, this is the same as taking representations of the fundamental group up to conjugation. So this is the monodromy data, and this is the compact Kähler variety. But you can also very well consider a K connection as a G connection in the complexification, and you have this, which is normally called the deformed space, which is the modular space of flat connections on the trivial principle G bundle this time. Also identified with a space of representations of the fundamental group. This time you should take an affine GIT quotient if you want to get an affine variety, but conceptually it's still the same. So this is what we've seen in several instances. And I will very briefly say something about the first row. So this first row that I have in this box, what you are seeing here are real symplectic spaces, okay? So the symplectic structure there was constructed by Atiyah and Bott using a more topological approach, and Goldman using an algebraic one. Then, moreover, these spaces are actually Kähler manifold if you choose a Riemann surface structure on sigma, essentially by the theorem of Narasimhan and Seshadri. And finally, using geometric quantization, this was quantized by what's called the spaces of non-abelian theta functions. So there is this, as you vary the Riemann surface structure, you have several spaces of quantization, you assemble them into a vector bundle, and then Hitchin and Witten, Axel and De La Pietra constructed a projectively flat connection there. So this is what happened for this first row here. That's all I want to say. This is just to recall some known material. What about the complexification then? So in the complexification, we have complex symplectic spaces. Now they are not real. You have actually holomorphic symplectic manifold. You should take the smooth locus, so you should maybe take irreducible connections and so on, but loosely speaking, this will be complex symplectic spaces. If you now fix a Riemann surface, they will not be Kähler, but rather hyperkähler. Due to the work of many people, this is the non-abelian Hodge correspondence on curve. And that's why I use the term DR, the deformed space, in the terminology of Simpson. And this time I will just say that geometric quantization can be done, but it's harder because you don't just have a pre-quantizable real symplectic manifold. You have some complex ones, so you have to work a little bit more. You could do deformation quantization, or if I want to say something about geometric quantization, I will just quote works of Witten, and then Jörn Andersen and former collaborator students of his, Nils Gammergård, Alessandro Maluza, and also myself, where somehow the geometric quantization was considered either for real or for Kähler polarizations. So this is somehow complex Chern-Simons theory, the quantization of that. This is again just to give a very brief review of this here, which does not want to be inclusive, and it's also of course not quoting all people that have worked on this by any means. But the punchline is that what happens here is that basically you choose some further structure on the surface. Here it was a complex structure or a conformal one, so a structure of Riemann surface, in some space, let's call it B. So for instance, natural choices are to take the whole of the moduli space of genus G compact Riemann surfaces, or maybe to take the universal cover Teichmüller space. So for each of these structures, you had some moduli space there, which is Kähler, and then after quantization, you had some Hilbert space. Or maybe it was hyperkähler, and then it is slightly more complicated. But what is still true is that the moduli spaces assemble into what's called a local symplectic system. So this diagram here, as I vary the Riemann surface structure, I have moduli spaces of flat connections or representations of fundamental groups, which all assembles into fibration of symplectic manifolds over the space of deformation. And this MB here is the character variety, which is just the Betti space that I had when I was considering representations of the fundamental group. Okay, so this is what you get if you consider monodromy data. So you vary those and you get some symplectic fibration over some deformation space of Riemann surfaces. To be totally explicit, what do I mean by a local system? I mean a symplectic fiber bundle. And then if it's a local system, then I should have canonical fiber-wise isomorphisms up to the monodromy of the base group. So what I have is a flat connection, okay? It's a flat Herassmann connection on this fibration, and it is symplectic. So if you integrate it, you get symplectomorphism fiber-wise. This is the mathematical way to express what Goldman referred to as the symplectic nature of the fundamental group of surfaces. So this Kähler structure is not topological. It depends on the Riemann structure, but the symplectic structure is topological. This only depends on the topology of the surface. So that's exactly saying that you have a local system. And so this is the classical theory, and the quantum theory then is just replacing this local system by a local system of vector spaces, which is just a projectively flat vector bundle. Okay, I mean, flat is the correct notion, but quantum mechanically, usually projectively flat is all that you can get, and also all that you care about in terms of the phase spaces. So if I should somehow summarize this known story, there is some fibration of symplectic manifolds, these moduli spaces, and after quantization, there is a certain projectively flat vector bundle. And in both cases, you have some monodromy action of the fundamental group of the basis. A flat connection has a monodromy, and so you can take it. In this case here, I had the Riemann moduli space, so the action would have been that of the mapping class group. So you get the mapping class group action of the character variety, or the quantum mapping class group actions, which have been studied quite a lot, as I said, in the past. This is somehow for me the known theory, although of course there is still work in progress in lots of directions. What I would now to consider, so part one of my talk is actually trying to introduce singularities. So singularities means that I am going to have essentially poles within the connections that will be simple or higher order poles. Let me show you. So I use the following identification. So note that if I consider smooth flat connections on a bundle over sigma up to isomorphism, that's actually the same as considering holomorphic connections up to isomorphism, where now sigma is a Riemann surface. And this identification here is just related to extending the scalars in the bundle you're considering, and maybe taking the 1-0 part of the connection. So this is somehow elementary. What is less elementary, but still true, is that considering holomorphic connections is also the same as considering non-singular algebraic connections, where now you consider sigma as a smooth, complex projective curve. So this is essentially the statement, one of the statements of this correspondence géométrie algébrique, géométrie analytique of Serre. So I can as well reason with the modular spaces of algebraic connections or holomorphic ones. And now what I want to do is, instead of having non-singular objects, I would like to have singular ones. This is the take-home message, is that if you add the singularities, you will have much, spaces which generalize by a lot spaces of representations of fundamental groups of surfaces, and their quantizations mathematically is still very much an open problem, as far as I understand. Although there is a lot of work in physics and in mathematical physics, of course, that's been done already. So let's see how to introduce singularities. Let me recall very briefly that, so I have singular algebraic connections, or which is the same meromorphic one. So let me recall that a regular singularity for a connection which is defined on a certain bundle over a punctured curve, this sigma O is a curve where you have removed some puncture and you have a connection defined there, you will say that this point A is a regular singularity if horizontal sections have at most polynomial growth as you go towards the puncture. So you write the equation nabla psi equals 0. This is the equation, this is a system of, in some trivialization, is a system of linear ODEs with meromorphic coefficients. And then you take the limit of local solutions as you go towards this puncture. What is the growth behavior of this psi? Well, if it's at most polynomial, then it is a regular singularity. But this is actually the same as having simple poles. So equivalently, what I'm saying is that I have an extension of the bundle across the puncture and an extension of the connection as well, such that I can choose a local trivialization around this point A, and I find a simple pole. So the connection is going to be locally given by a meromorphic one form with value in the algebra. And this is going to have a residue term, lambda over z dz, say, for some element lambda in the algebra. And then something which is just holomorphic, so some converging, power series with values in the algebra. And here, of course, I'm choosing some local coordinate vanishing at the puncture to write in this way. So this is what a regular singularity looks like. And to just say a few words, loosely speaking, as to how one should expect then polynomial growth, essentially, local solutions, very loosely speaking, without being, without giving all details and all terminology, local solutions will look something like you start from some initial condition psi 0, and then you have this term z to the lambda, which is a function defined using a branch of the logarithm. So you choose a branch of the log, and then you can define this z to the lambda using the exponential, of course. And this is basically a solution up to some holomorphic term in general. So you see that this is what carries this polynomial growth. And moreover, this is what gives you the monodromy, because you chose a branch of logarithm. So if you move around the simple pole, there's going to be some monodromy, and that's exactly the representation of the fundamental group that you get from this regular singular connection. Okay, so this is the first thing you could do. But then we can do more. So importantly, the theory has already been, described mathematically for irregular singularities. So please consider the following case. So instead of regular singularities, I want to consider irregular one. So they will be characterized by those such that horizontal solutions have an exponential growth or decay behavior as you go towards the puncture. And this is equivalent to saying that locally, the one form defining the connection has an additional term, okay? You don't just have the residue and the holomorphic part, you also have something with higher order poles. And this I can write compactly as the differential of some meromorphic function, this function q that you see here. So Q here is a meromorphic function with value in the algebra G, which is only, you know, which only contains negative powers of Z. So you can very well think of it as an element of the loop algebra up to positive currents. But this is, as I said, just a G-value meromorphic function. And here, the integer p is going to be the order of the pole. So this is some positive integer. Here I sum up to p minus 1, because then I take the differential here and I get to a pole of order p. So this function is defined by some coefficient ti that live in the Lie algebra I've chosen. So this is what I want to have a look at. I want to have a look at connections which locally, in some gauge, I can write like so. And so essentially, to say what is going to come in what, you know, in what's going to happen, essentially what I will do is that I will have moduli spaces where I have more parameters than usual. I will not just have the complex structure of the surface, I will also be able to move the position of the irregular singularities. So you can move the positions of the poles. And then essentially, I will allow myself to be able to move this term here. So to vary the leading irregular coefficient. If you vary these parameters here, this ti, you are varying the principal part of the connection, and you have new moduli that give you new interesting deformations when you want to construct moduli spaces of meromorphic connection. This is somehow the main new feature in the classical case. Okay, again, if I want to say just a few words about how solution should be exponential, again, local solution, so locally solution will be written as still a polynomial term involving the residue, or I should say the formal residue, but okay, let's loosely speak. And then you will have some dominant, some leading part with exponential behavior, which is now this function related to this irregular type Q. So this is what's going to give you these solutions. And that's what gives you the exponential behavior. And now you don't just have the monodromy as you go around the puncture, you have more. You also have certain directions in which Q is going to have maximal or minimal decay or growth. And these are called singular directions. And this is what Stokes introduced. So these are the Stokes state of this connection, which are more than just the representation of the fundamental group of the surface. So that's why I say we are going in a deeper, you know, context, because it's not just enough to have the representation of the group. You also have to understand Stokes data to reconstruct the connection completely. So we have moduli spaces which are much richer than what one has if one only considers regular singularities. Okay. So the only definition I will give today is that of an untwisted irregular type. So I will not consider any possible principal path. I will restrict to those Qs such that all coefficients are you know, simultaneously diagonalizable, essentially. So I am asking that this is actually a Cartan valued meromorphic function for a fixed Cartan subalgebra that you've chosen. Of course, in the case of SLM, you would have diagonal traceless matrices, but it'd be okay, whatever other root system you can imagine, and so on and so forth. So this is what I consider. I'm not taking any possible singularity, but just singularities such that in a certain gauge, I can somehow diagonalize all the coefficients, which is possible generically. Okay, this is not always true, but generically, this is what's going to happen. So it's not so much of a restrictive hypothesis. And then essentially, I would like to have a look at another diagram, which is the generalization of what we had in the previous part. So now I fix mark points and I fix these irregular types, an n-tuple of those. So irregular types fixed at each one of those at each of these mark points. And then you now can consider new moduli spaces. So these deformed spaces, which are either regular or irregular, depending on these parameters. The first one, which are just still related to representations of the fundamental group of the surface, while the second one are the new somehow that I'm really interested in, and they are generalizing spaces of representations. So the first row, to be totally explicit, the first row, this regular singularity case, these are moduli spaces of connections where I just ask to have simple poles at the given punctures, and that's it. And a theorem tells us that they are naturally Poisson spaces. You can make them smooth again by choosing some generic parameters, and you can make them symplectic if you restrict the residue to live in certain orbits. Analogously, if you want on the viewpoint of representations of the fundamental group, you should instead restrict the monodromy to lie in certain conjugacy classes. But nonetheless, what you get is just the complex Kähler varieties. So it is still just spaces of representations of fundamental groups. The second row, however, is the following. So the second row is the modular space of connections where, yes, I have poles there, but now I use the irregular type. So now I allow for higher order poles, and I ask that in some local trivialization, the principal part should be controlled by this meromorphic functions Q that I had above. So in some trivialization, my meromorphic one form must be written as dq plus lambda z over z plus holomorphic terms. This is what I am requiring. I am considering modular spaces of connection with prescribed positions of singularities and this behavior for principal paths. And what's interesting is that this a priori is a more complicated problem to consider. I mean, it is, but the mathematical theory is already perfectly been set up in the same language as above. So it is still true that this is a Poisson space, and it is still true that you can make it symplectic, so you can realize it by a Hamiltonian reduction, analogously to what we know from the non-singular case. And moreover, this is identified to the modular spaces of Stokes data, just as before I had the spaces of monodromy data, which were just the representations. And these are what Philip Bolch calls the wild Kähler varieties. Okay, so now they can be obtained using a quasi-Hamiltonian quotient. I am quoting this paper of Philip 2014. The title of this paper was Geometry and Braiding of Stokes Data, Fission and Wild Kähler Varieties. But so this is the geometry of Stokes data we are talking about. This is the quasi-Hamiltonian geometry of Stokes data, which gives you this new huge family of symplectic manifold that you can try and consider. And now the second ingredient is that I also want to have deformation spaces and get local systems, and then I can try again to have quantization. So we also have this. That's also been done. Okay, so what about deformation spaces? Well, in the regular case, I think you agree that I can vary just the Riemann surface structure as above, but I can also vary the punctures. So essentially, I get the modular spaces of pointed and pointed compact genus G Riemann surfaces, MGN, okay? Or maybe they're universal covers again. So nonetheless, you have some symplectic local system as above, symplectic local systems of modular spaces of meromorphic connections or Kähler varieties. You have the monodromy there, and after quantization, which is essentially analogous to what we have above, we have the quantum action of the fundamental group. But what about the irregular case? So that's the point. Now I have more. Now, as I said a few minutes ago, I have new moduli to deform. I have these deformations of the irregular types. So now I should consider triples consisting of Riemann surface, an n-tuple of mark points, and an n-tuple of irregular types, this sigma underlined that I have here. So this is also known as a wild Riemann surface, also terminology of Philip Bolch. And so now I move all of this. So more precisely, I define some deformations of those admissible ones. So for instance, the mark points should not coalesce and so on. And then you try and consider modular spaces. So essentially you will consider morphisms between such triples to be holomorphic maps between the underlying Riemannian manifolds, which preserve the mark points and which pull back irregular type one to another. Okay, the regular types were meromorphic functions, so you can just pull them back. And this modular spaces generalizes simultaneously this MGN, which is just the case where you have regular singularities. And even further, the space is MG, which correspond to the case where there are just no mark points at all. So you have new spaces of deformations. And now the last piece of classical, data is that you still have symplectic local system if you define deformations in this way, okay? So if you now say that for every choice of a wild Riemann surface, I have a modular space of connections, or of Stokes data. You can now vary the structure here to get a family of manifolds. And it is still a theorem that disassemble into a local system of symplectic manifolds. So you still have some flat symplectic connection there. This could be phrased as the symplectic nature of the wild fundamental group, an object which was defined by Ramis and Martinez before the 2000, I think. Or if again you want to stick with this paper of Philip I was quoting before, this is what he calls the braiding of Stokes data. So the geometry we discussed and the braiding is precisely this. So you can now move them and you will get some action of the fundamental group of the base because it's given by the monodromy of this connection here. So this monodromy is generalizing the action of, in particular, Artin braid groups and mapping class groups on the character varieties that we had in the usual setup. So this new connection here, because this is defined by asking that monodromy data should be fixed, this is called the isomonodromy connection. I mean, again, to be more precise, I am requiring that Stokes data are fixed, but so we just call it the isomonodromy connection. And so its leaves, the integrable manifold of this connection, are going to be precisely families of connection with fixed Stokes data. And this is the end of, this is all that I wanted to say about irregular singularities in the classical case. So this is how the theory has been set up in the past and how this could work to you know, how this already works to generalize all that we know about local systems of representations of fundamental groups of surfaces. So now the question I ask, the second, and I mean the last part of this talk is just quantize this, okay? So this is the punchline of this whole talk. After this is just going to be examples. The project, the main project we have is that we would like to take these local systems of modular spaces of irregular meromorphic connection and replace them by projectively fed vector bundles in such a way that, of course, each fiber is a quantization of the modular space we had before. Deformation quantization, geometric quantization, no matter. Let's try to have these vector bundles. And so note in particular that when I say flat, this is the problem. So the main task will be to construct the projectively flat connection in such bundle. Okay, so the connection which quantizes this isomonodromy connection. And then second, of course, once you have this connection, you could try and compute the monodromy, which will give you a quantum action of the fundamental group of the base, which again is some generalization of braid groups or mapping class groups. This is the main project. So said like this sounds probably very abstract because we have to use this intrinsic approach in order to make sense of deformations in a good way. We cannot just work with local trivialization, so that's not very explicit. And maybe it also sounds difficult, like, can you do this at all? And so in the next of the talk, I would like to give a few examples to make this more explicit, to show you the type of applications you can have, so explain why this is promising. And also to show that it's actually doable, like this has been done already. We know example where this actually happens, okay? So let me try and give you these examples. If I cannot go through all of them, it's not a big deal. The most important message is already on the screen, okay? So let's see a few examples. To see the examples, I will do the following. I will only consider surfaces of genus 0. So I am only on the Riemann sphere. And I consider actually the subspace of the modular space, which is defined by requiring that the connection live on a bundle which is holomorphically trivial, okay? So all bundles should be topologically trivial because of the topological hypothesis I had on the group, but now I also want them to be holomorphically trivial. So the advantage is that now I can give a meromorphic connection by a global meromorphic form. So this is what I'm going to do. And you will see that it's already very rich, both from the geometric side and on the quantum side. So let's start from the first example, which should be the regular case. So let's see what happens if I just have simple poles. Consider, please, the connection defined by this one form A. So I just have a few residues and positions of poles Ti. So here I am taking just a coordinate to identify CP1 with the complex plane and then a point at infinity. And so here you see the deformations that I have. Basically, I can just vary the position of the poles because I want them to be simple. So I do not have these deformations of the principal path to consider. So my base space is just configuration space of points in C. And to be sure that I have no pole at infinity, assume that the sum of the residue is 0, okay? So that really all poles are at finite distance. And now to go on, the first fact that enables us to go on is that there is actually a very easy description of this modular space of a meromorphic connection of this deformed space with a star. This is just a product of orbits for the group and then complex symplectic quotient at 0 with respect to the action of G. This is just taking the gauge action of the holomorphically trivial vector bundle, and the orbits, which are where the residues live, they can be adjoint or coadjoint. Doesn't matter because I'm going to use a non-degenerate pairing on the Lie algebra to identify them. So the local system I had before, this system of symplectic manifold here, actually comes with a global trivialization because this space here clearly does not depend on the position of the points. So I have a global trivialization. And actually, one can show that the isomonodromic connection is nothing but a certain Hamiltonian system. Okay, so there is a certain integrable Hamiltonian system, which is, found by Schlesinger, basically 100 years ago. So it's placing a system, this Hamiltonian system here. So where I take an n-tuple of residues and the position of the points, and I have this function here using an invariant pairing on the Lie algebra, as I was saying. So you can think of the killing form for a semi-simple Lie algebra or just the trace if you were using GLM, for instance. And it turns out that the flow of this Hamiltonian system on this Poisson manifold using the Poisson-Lie bracket of G star is exactly is controlling the isomonodromic deformations. So this is what we have. What about the quantization? Well, this is straightforward. So I'm just going to think of these Hamiltonians as functions from this base space into the symmetric algebra of G, or rather a tensor power, because G is equal to G dual, and this is the space of algebraic functions on that space then. And then I just take the canonical symmetrization map from the symmetric algebra to the universal enveloping algebra. So a version of deformation quantization, filtered deformation quantization if you want, to construct some quantum Hamiltonian. So what you get is this Hamiltonian HI hat that you will see in a while once this updates. There you go. These Hamiltonians here, which involve the action of the canonical quadratic tensor of the quadratic Lie algebra, okay? The tensor capital omega, given by summing over an orthonormal basis of the Lie algebra, acting on the ith and the jth slot. So this is a straightforward computation using essentially the PBW theorem. And then you will recognize up to this constant that these are the Hamiltonians for the KZ connection, right? So this was first observed by Reshetikhin and Harnad, although not in the simple way that I am phrasing it, that the KZ connection arises as a quantization of the Schlesinger system. Of course, if you take good constant, so you should take a level for the action of, the central element of the affine Lie algebra of G, and then the dual Coxeter element here. But up to that, it's exactly the same. It's the KZ connection. So this is the quantization on this bundle, quantizing this symplectic local system. And the monodromy has also been taken already. So here, the monodromy was shown by Kohn and Drinfeld to be equivalent to the representation of the braid group arising from the universal quantum R matrix of the Jimbo-Drinfeld quantum group. Okay, this is the Kohn-Drinfeld theorem. So we already know what the monodromy should be in this case here. And this is the first example I wanted to make. What about another example with irregular singularity? Well, here, let's consider, please, another case where I take a form like T plus lambda over Z dz, also on the trivial bundle over the sphere. So here, T is in the regular part of the Cartan subalgebra. So think distinct eigenvalues in the case of SLN. And so now this carries a pole of order 2. So T is now an irregular type that I didn't have before. So now I see these new deformations. Namely, the deformation space is precisely that of variations of t. And again, one can show that there is some isomonodromy system giving the deformations, where now you have as many Hamiltonians as the rank of the algebra, so the dimension of the carton. And the quantization and the monodromy have also been taken. So the quantization gets you the Casimir connection, as shown also by Bolch in a paper of 2002. And the monodromy was instead computed by Laredo to find an analog of the Conner-Drinfeld theorem for quantum Weil group. So this quantizes the action of the classical action of the quantum Weil group of the Concini, Katz, and Procesi. So again, everything has been done here: quantization, monodromy, and so on. Two more examples I wanted to give, actually three, so very briefly. Another example that I can give is combining the previous two. So you can take still some pole over the two, but now you can take several simple poles. And so now here you have the base space, which is going to be the product of what I had before. You can move the positions of the poles and also vary this irregular coefficient. Then the classical isomodromy system is due to Jimbo, Miwa, Mori, and Sato. And the quantization gives you another connection introduced by Felder, Markov, Tarasov, and Varchenko. This I showed myself. And the monodromy uses some quantum version of Stokes matrices instead. So this is somehow the combination of these two. Another example, very briefly, I will skip through this by just saying that I can now add a term like this. You see A times Z. So now I can put a pole over the 3 at infinity. I will have several components for the deformation spaces, where essentially I can vary all the spectra of this semi-simple matrices A and T here. So you get something which is called the simply laced isomonodromy system in the classical case, and the simply laced quantum connections after quantization, also in the deformation quantization picture. And the last example I wanted to make, so this is more recent work. So this was also done by myself. This simply laced quantum connections was one of basically the project Philip proposed me during my PhD thesis. And then a more recent work, we can now consider arbitrary singularities, but I only vary the positions of the poles. I am not varying the irregular types. The classical system is then due to Bernard Clares, and it was Reshetik in itself back in the same paper as before who explained how to quantize this. And so now we have a work with Giovanni Felder, where we actually defined irregular conformal blocks, so a version of conformal blocks presence of irregular singularities in the Wess Zumino Novikov Witten model, generalizing Verma modules. And then we are able to just use the Sugawara operators to give a quantum flat connections as you vary the positions of these poles, which is exactly in view of the project above, another example of this quantization of local systems of symplectic modular spaces. So the summary is this one, basically, what I showed you about these genus 0 examples. You have the Schlesinger system, which gives you KZ configuration of points and several simple poles. This dual case that gives you the Casimir connection after quantization and just one pole over the 2, one pole over the 3. Then this Jimbo, Miwa, Mori, and Sato quantization with the connection of Felder and collaborators with one pole over the 2 and several simple poles. Then the simply laced isomodromy system, where now you can have a pole over the 3. And finally, this system of Clares, where you now can have arbitrary singularities, but where I am just moving the positions of the poles. So short-term projects here would be to compute the monodromy of these two last connections here. So this, as far as I understand, has not been done. So there is a nice short-term project here to understand what the monodromy looks like here. And then another, possibly even more interesting, is to extend this connection here. So the last part, the one for arbitrary singularities, to extend it so that I can now also deform not just the positions of the poles, but also these irregular types, the coefficients of the meromorphic connections. I thank you for your attention very much, and I will stop here.
So are there questions at this point?
Yeah, thank you very much for this nice talk. I have one very so singular connections. There are these terms where you said there's this polynomial solution, z to the power of something.
Yes.
If you use a branch cut.
Yes.
You look at, I'm asking for, if you look at this construction of Drinfeld associators, I mean, they appear, but I mean, people compute this like functions, and they are not functions. So could you just say some well-educated words?
No, right. Yeah. But your words were already well educated. Yeah. No, sure. You're right. So these Drinfeld associators are there, I think, precisely in this case of regular singularities, but I still don't know enough about this to say more. But so this Drinfeld associator, I understand as being one way to compute the monodromy of Kz, essentially. So what I'm saying is that you have the classical solution to the equation nabla psi equals 0. Where nabla is this connection with logarithmic singularities, and the solution are the tau functions. And then what you want to do is that you want to consider the quantum connection. So let me put a hat here. So this would be Kz essentially. And I also want to understand how this equation, so how the solution to this equation looks like, because that's exactly what you need to do to compute the monodromy of this connection here. You want to say, I fix a point, I have a local solution, I analytically continue it, and I see how the fiber transforms from one point to another. And so here you get quantum tau functions, or I mean, however you want to call them. So these are the correlation functions in this correlation functions in the WZ and W model. And I think the Drinfeld associators were used, are another tool that one can use here, are like a finely algebra theoretic tool one can use to explain how such solutions transform after you analytically continue around one singularity, which is exactly what you want. You take a loop. So a loop is just a braid in this case, right? Because you're braiding the position of the points. You do this, and then you can move from one solution in this branch to the other one by using these associators there. And this is exactly what enabled, I think, Drinfeld to prove Kohner's conjecture about the monodromy of Kz. But I don't know how one would use this in the irregular case, though. So there is this basic idea that one could try and make sense of irregular associators to try and compute the monodromy where you have higher order poles. So I don't know about that, however.
This answers already my second question. So will you have any hopes to do some irregular associators whereby using this in your table, the last line of the irregular KZ?
Yes. So right. So this is what I might hope to do. So what I might hope to do is the following. So no, wait, let me be precise. So you asked, do I hope to do some? Yeah. So right. So there is the project to try and make sense of those. In this case here, sure. So this is what I hope to do. What I can say is that I have some strategy instead, not to compute the monodromy, but to do this other stuff here. So not just to vary the positions of the points, but to also consider deformations of the irregular types. And this hopefully might give some hint as to how also compute the monodromy along these other deformations, right? And what I hope to be able to do is that there is something which is called the Harnett duality, the Fourier Laplace transform. Here you see that I've written Schlesinger, and here I've written dual Schlesinger. And so there is some transformation going from one to another on the classical world, which has a quantum analog. So this in the quantum world is the How duality, I think it's called. And so what one hopes to be able to do is that I take this system here and I try to compute its transform. So getting something new here, getting some new system where now I am varying these irregular types. And then you hope to be able to somehow quantize this transformation here to get some new flat quantum connection here along these deformations. And then once we understood that, maybe it will be clearer how to use the KZ associators to try and construct the irregular one once you have the full connection here. But I mean, this is all, yeah, I don't know. It's work in progress.
Thank you very much.
More questions? Not seem to be the case, so let us thank Gabriele again. And many thanks to all our speakers of the day. Thanks to everyone for attending, and see you.